All right, well, welcome back to part two of our kind of cute little intro to the graphing world. So in that last section, or the first part of this intro section, we were chatting a little bit about different ways to encode some of these cute little graphs. And along the way, I mentioned one technique that we did not have in that previous section that we're now going to kind of poke into a bit farther, which is going to be storing these nice little graphs in what's referred to as an adjacency matrix, or in this really big array. So to start things off, we're going to need a graph. So here we're going to have this really nice, small, cute little guy, which happens to have exactly 4 vertices and what, 5 total edges. This particular graph is very close to being what's referred to as complete. It's almost got everything that you would ever want it to have, except for it's missing this one little edge from 0 to 3, which is totally fine. It's just missing that one. So those two nodes, whatever they're going to represent, are just currently lacking. So last section, we represented these things through these nice little dictionaries, or kind of this big structure of lists of lists. We're going to have the 0. We're going to record what the 0 happens to be adjacent to. We're going to ask what its neighbors happen to be. So here you can see that 0 is connected to 1 and 2. Great. Awesome. Cool. So before, we would have stored that as this little term with the 1, 2. What we're going to do now is we're going to switch this to this giant array structure, or this big adjacency matrix. So just like before, we're going to look at this little graph of 4 vertices. They are currently numbered 0 through 3. So what I'm going to do is I'm going to morph this over into this big 4 by 4 box. I'm going to label the rows and the column of this box with exactly those labels of those vertices off on the left. So I'm going to have 0 through 3, as well as 0 through 3 over there. And then you're going to see that each of those little things are then going to correspond to some specific element inside of that. There's basically going to be, a 0, 0 term, a 0, 1 term, a 0, 2 term, and a 0, 3 term. Whether or not that thing blips as a 0 or a 1 is going to talk about whether or not those two nodes or vertices are actually adjacent to one another. So the 0, 0 thing is not going to blip as a 1 because 0 is not adjacent to itself. A little bit later, we'll start chatting about what does that mean if I kind of have a loop on itself. But right now we don't have that, so that's going to correspond to that little 0. We do have 0 connected to 1, which is going to show me putting a little 1 right there. Because this graph doesn't have any directionality or specific flow, you can see that if 0 is connected to 1, then obviously 1 is connected to 0. So this ultimate little array that we're going to form is actually going to be nice and symmetric. So the 0, 1 term, as well as the 1, 0 term, those are going to blip as being the exact same thing. You can see that 0 is connected to 2. Therefore, 2 is also connected to 0. So those are going to blip as little 1s. And lastly, that 0 not being connected to 3 is then going to represent 0s in the top right corner, as well as 0s in that bottom left corner. After that, you can kind of fill out the rest of this thing pretty easily. Obviously, 1 is not connected to itself. It is connected to 2, and it is connected to 3. So 1 and 2 are obviously connected to everything except for themselves. So you're going to see that on the 3 side, it's going to look very similar, except for the 3 is obviously not connected to the 0. So we're going to get this big diagonal down the middle of all of these 0s because there's no little self loops, and then some sprinkling of 1s and 0s throughout the rest of this thing. So I'm currently drawing this as this nice kind of big array, but obviously this is just going to be viewed as a list of lists. So I'm going to have that first list, which is going to be those entries 0, 1, 1, 0, and then so on and so forth. These things can grow fairly quickly. Obviously, if my network has 10,000 nodes on it, then this adjacency matrix is going to have 10,000 rows and 10,000 columns. So there's going to be a whole bunch of stuff inside of it. And that's kind of the point of today, is that we're going to transition to this. We're going to chat a little bit about what we can do with this adjacency matrix. And then really we want to begin dwelling on how we can do those things efficiently. That's kind of the game that we're trying to poke into a little bit more than you would have seen in previous classes, is that we have this thing, we can do some stuff, but now I really want to dwell on questions of how do I do that as efficiently as possible. So the first thing that we want to start doing, well, I guess here's the fancy definition for an adjacency matrix. Hopefully that example made sense. This probably makes far less sense, but there it is. It's a fancy definition. All right, so the first thing that we want to begin looking into, which is obviously building off of that question from that first section, is going to be asking questions of reachability as well as kind of what is the minimum number of paths or minimum length of a path that I can get to from a starting place to a stopping place. So what I want to do first is basically broaden it from paths of length 1, which is essentially what the adjacency matrix is doing. It's going to represent, is there a path of length 1 from starting place to stopping place? If it blips true, then obviously you have it. If it blips false, then you obviously don't have it. What I want to do now is I want to increase the length from length 1 to length 2. So I'm going to basically begin asking, where can I get to in exactly 2 moves at a variety of different starting places? So I could think about how many paths of length 2 are there that start at 0 and let's say end at 3. So I'm capping this specific length is that I have to use exactly 2 clicks. So to get to 3, I can obviously go around the bottom or I can go around the top. So I have exactly 2 of those things. Likewise, if I want to think about paths that start at 0 and end at 0, I have exactly 2 of those as well. I can go to 0 and then come back, or I can go to 1 and then come back, or I can go to 2 and then I can come back afterwards. So I have 2 paths of length 2 that start at 0 and end at 3, as well as start at 0 and end at 0. They actually kind of function very similarly. They both leave 0 and they either keep on going to the 3 or they run back to their home. If I wanted to have a different starting place, I could start at 2 and ask basically the exact same things. How many paths of length 2 are there that start at 2 and let's say end at 2? Well, here you have the dumb ones, the out and back, out and back, out and back. So I have 3 of those. And then I can think about, okay, well, what happens if I start at 2 and end at 1? Well, you can go around the top part or you can go around the bottom part. So you're going to get 2 there. So ultimately, I want to start storing all of those specific numbers in another nice little adjacency matrix-esque thing. Basically, another list that happens to have 4 rows and 4 columns. And I'm going to label this thing A2, which is going to be somewhat suggestive as to how we're actually going to build these things up. But for right now, we're just going to store this as how many paths are there. So paths of length 2, which is the exponent on this notation, that start at 0 and let's say end at 0. We knew that there were 2 of those, basically the out and back. If I start at 0 and go to 1, well, there's only one way to do that. Likewise, there's then one way to go from 0 or from 1 back to 0. And I started drawing, so I won't be able to just hit back. All right, so what about starting at 0 and ending at 2? So we have go around to 1 and then back down to 2. So there's 1 of those, which means that there's 1 from 2 back to 0. And then starting at 0, ending at 3. That's the one that we chatted about before. So it's kind of going around the top part or going around the bottom part, which is going to mean a 2 here and a 2 there. All right, what happens if we start at, let's say, 1? So if we start at 1 and end at 1 with exactly 2 clicks, that's kind of the dumb out and back, out and back, out and back. So I'm going to get 3 of those. If I start at 1 and end up at 2, you can see that you can go around the top part or you can go around the bottom part, which is going to mean 2 of those things, which means 2 of those things. If I start at 1 and end at 3, there's only one way to do that, which is 1 down to 2 over to 3. Likewise, from 3 to 1 would be the exact same thing. All right, what about 2? So 2, starting at 2, ending at 2. So that's out and back, out and back, out and back, which means I have 3 of them. What about 2, starting at 2, ending at 3? I think there's only 1 for that, which is going up to 1 and then back down. And then I get a 1 there as well. And last but not least, we have starting and stopping at 3, which is going to then just be a 2. Here you can actually see that this diagonal of a 2 is actually going to give me the degree of all of those nice little vertices. Obviously, they're all going to record those out and back, out and back, out and back, as long as I don't have any of the dumb little spinny loops on things. So we have A, which is my starting place, which you can actually kind of think about as A1, which is going to record paths of length 1 that start at some vertex I and end at some vertex J. Here we then have A2, which is going to record paths of length 2 that start again at some vertex I and end at some vertex J. So here would be your I's, here would be your J's, and you can easily record those. And then after that, basically the sky's the limit. You can start computing, let's say, A3. So A3 would then be paths that would start at some given vertex, and I want to begin counting paths of exactly length 3. So let's try to, like, say, build up maybe the first row of this thing, and then I'll kind of show up what the rest of it would be. So I'm going to have 0, and then 0 can go to 0. That's not a 0 at all. 0, a 1, a 2, and a 3. So paths of length 3 that start at 0 and end at 0. Here you can see we actually can't do it. Basically, if you leave 0, that's going to take 1. Nope, actually I lied. There is 1. I totally just didn't see it at first. Man, I'm really bad at counting sometimes. It's really hard. Because, all right, let me double back on that. All right, so paths that start at 0 and end at 0 that have length 3, because I have this nice little connector, and I can go around that 2 different ways. So I can go 0, 1, 2, 0, or 0, 2, 1, 0. You can see that I actually get exactly 2 of those. I was thinking for whatever reason, I was starting at 1 or 2 where I didn't have nice little connections. Obviously, if you're starting at, 2 and I wanted, oh, that would still work too, because there's a dumb triangle there. Never mind. There's going to be a later discussion on that, and I'll recircle back on that. But this one's going to have numbers all over the place, so forget what I just said about having possible zeros. All right, so let's start at 0 and now end at 1. And I want to think about paths of length 3. Yuck. All right, so we get kind of the standard one, which would be going around the bottom. What else do we got? I can go to 1, and then I go back to 0, and then back to 1. And I can basically do that in a couple different ways. I can go to 1, I can go down to 2, and then back. Or I could go 1 down to 3, and then back. And I guess I can go down to 2. Oops. So I can go down to 2, up to 1. Nope, that one doesn't work. So we got what? The blue one, the yellow one, the green one, and the purple one. I think there's one more. So if I can do this one. So I can go 0 to 2, back to 0, and then run over to 1. So I do in fact get 5 in that capacity. Yuck. All right, let's get rid of all that junk. All right, so what's next? We have starting at 0, ending at 2. Well, because of some symmetry, that should be exactly the same. Basically, the 1 and the 2 function nearly identically. So it's going to be a 5 as well. So then the other one is how can I get from 0 to 3 in exactly 3 moves? Here I can go and do kind of this crazy Z shape, S shape, depending on how it looks, or I can do the reverse version of it. So I'm going to get 2 of those as well. All right. Obviously can't count, so I'm just going to stop there because counting is hard. And we're going to be like, voila, hooray, here's the nice little matrix. It does all the things that it needs to do. Hopefully the top row of that thing is exactly what it's supposed to be. So we have, again, this structure of A3, which is then going to keep track of paths of length 3. That first row, the 2, 5, 5, 2, then should obviously be identical to the very first column of that thing because there's symmetry going on. If I start at 0 and end at 2, well, whatever path I get, I could start at 2 and then go back to 1. So that's where we're going to be playing around a little bit. Obviously, in my inability to construct these things by hand, we're going to want to think about automating this process and how we're actually going to go about computing these things. And then we're going to start chatting about how we can do that efficiently and then really begin kind of blasting these things to massive powers. So it'll slowly snowball on itself, but the idea is that counting things by hand here is really hard in that I obviously mess up a few times. And thinking about our future example swayed my ability to actually construct them, but hopefully you can count these things fairly easily. And now we'll jump into how we actually want to do it.